Greetings. Today we're taking a deep dive into, well, the fundamental nature of sound.
Yeah, it's a fascinating topic.
It really is. And Zoran's concept of sound as the universe's own tongue, that really stuck with me.
Mm,
So that's our focus today. Trying to understand sound, not just, as something we hear, but maybe as this key force throughout the cosmos.
absolutely. And we're using Zoran's insights sort of as our guide here, pushing beyond just the everyday experience.
Right, exploring the mechanics underneath it all.
Exactly. So our mission, if you like, is to unpack the essentials. We're talking sound waves, frequency measured in hertz, amplitude in decibels, wavelength.
And how the medium, the stuff it travels through, really shapes what we perceive in the end.
Precisely. It's all interconnected.
Okay, so let's start simple. Or, well, maybe not simple, but fundamental. Sound as a wave.
Right. So at its core, sound is a mechanical wave. And what that means basically is it needs a medium. It needs stuff to travel through.
Like air or
Uh,
water.
Or solids, yeah. Think of dropping a pebble in a pond. You see those ripples spreading out.
Sure, the disturbance travels.
Exactly. That disturbance, that initial vibration, creates a wave that propagates outwards. Sound works much the same way.
So it's different from light then, because light travels through space, doesn't it?
That's a key difference, yeah. Light is an electromagnetic wave. It doesn't need a medium. Sound absolutely does. No air, no sound.
Got it. So when something makes a sound in air, let's use Zoran's example, like vocal cords vibrating,
Mm-hmm.
it's pushing the air molecules together in some spots.
Correct. That's compression. And then in other areas, they spread apart a bit. That's rarefaction.
Compression, rarefaction, back and forth.
And that back and forth movement, that vibration, is happening in the same direction that the sound wave is moving,
Okay.
which is why we call it a longitudinal wave. The classic analogy is like pushing one end of a slinky. You see that compression travel down its length, right?
Yeah, I can picture that. But the slinky itself doesn't fly across the room.
Exactly. That's crucial. The individual air molecules, they don't travel from the source to your ear. They just sort of oscillate. They wiggle back and forth around their positions.
Ah, so they bump into their neighbors.
Precisely.
Yeah.
And pass the energy along. Like, think of a line of dominoes.
Right, you tip the first one.
And the fall travels down the line, but each domino just falls over where it is. It's the energy propagating, not the dominoes themselves moving down the line.
That makes perfect sense. It's the energy wave moving through the air.
And Zoran even hints at this deeper level, subatomic, saying these sound waves kind of impose an order on the random jiggling of molecules, the thermal motion.
Helping the energy transfer more efficiently. Interesting.
Yeah, it adds another layer.
Okay, so that's the wave nature. Now let's talk about frequency. You mentioned frequency, the pulse of the sound wave.
Exactly. Frequency is all about how fast those vibrations are happening. How many of those compression rarefaction cycles complete in 1 second?
Right, okay.
And we measure that in hertz, abbreviated hertz.
Mhm.
So 50 hertz means 50 cycles per second.
So something with a low frequency, like Zoran mentions tectonic plates rumbling, or maybe a dragon's deep growl,
Yeah, a deep rumble. That means fewer cycles per second, slower vibrations.
versus the high frequency, like a bat squeak.
Right. Very rapid cycles per second, high frequency.
And it's amazing how Zoran connects this from like super low frequency gravitational waves, nanohertz, he says, all the way up to gamma rays, which are incredibly high frequency. It shows frequency isn't just about sound, is it?
Not at all. It's a fundamental property of waves across the universe. It really drives home that universality.
And he suggests a dragon's roar isn't just one frequency either.
No, probably a whole spectrum, a huge range of frequencies all mixed together, which is likely part of what makes it so, well, powerful and versatile in its effects.
And this frequency thing, that's directly related to what we perceive as pitch.
It is. Pitch is our subjective experience of frequency. Generally, low frequency sounds low pitch.
Like a bass guitar.
And high frequency sounds high pitch.
Like a flute.
Exactly. Zoran uses that lovely image, doesn't he? The cosmic harp.
Yeah, each string vibrating at its own frequency, creating its own note.
It makes you think, doesn't it?
Yeah.
The universe just humming with countless frequencies all the time, everywhere.
It really does. Okay, so frequency is the rate of vibration,
Mhm.
perceived as pitch. What about the power, the loudness?
Yeah. Now you're talking about amplitude.
Amplitude, right.
Amplitude is basically the measure of the energy the wave is carrying. It relates to how much those particles, the air molecules, for instance, are being displaced from their resting position by the wave.
So back to the pond analogy.
If you drop a tiny pebble, you get small ripples, small displacement from the flat water surface. That's low amplitude.
But if you heave a massive boulder in...
Then you get huge waves.
Hmm.
Much larger displacement. That's high amplitude. More energy involved.
And for sound, that displacement, that amplitude, is what we hear as loudness.
Directly. Small displacement, low amplitude, quiet sound. Large displacement, high amplitude, loud sound. Makes sense, right?
Yeah, it does. And we measure this using decibels.
And that's the one, decibels. Zoran gives us those handy reference points. A whisper, maybe 30 dB. Normal conversation, around 60 dB.
A rock concert getting up towards what, 110 dB?
Yeah, getting pretty loud. And then he hints, a dragon's roar would be, well, off the charts for us. Immense amplitude.
I bet. Now, he also mentions the decibel scale is logarithmic. Why is that?
Well, it's because our ears can handle an absolutely enormous range of sound intensities, from the very faintest sound we can detect to sounds that are incredibly powerful.
Billions or trillions of times more intense.
Exactly. Trying to use a linear scale for that would be really unwieldy. The logarithmic scale compresses that huge range into more manageable numbers.
And it also kind of reflects how we perceive loudness, doesn't it? Like a 10 dB increase sounds roughly twice as loud to us.
Pretty much, yeah. It relates to that principle, the Weber-Fechner law, about how our perception relates to the physical stimulus change. It's quite clever, really.
So frequency and amplitude are distinct but related.
Definitely. You could have, as Zoran might put it, a tiny, rapid quiver that's high frequency, but low amplitude, a high-pitched whisper.
Or you could have a massive, slow undulation, low frequency, but high
A
amplitude.
deep, powerful roar. Totally different characteristics, different impacts.
Okay, this is clicking into place. We've got the rate, frequency, pitch, the power, amplitude, loudness. What about the physical size of the wave in space?
That brings us to wavelength.
Wavelength, lambda, right, the Greek letter.
That's it, lambda. Wavelength is the physical distance between two corresponding points on consecutive waves. So from the peak of one compression to the peak of the next one.
Or from one rarefaction to the next.
Exactly. It's the wave spatial dimension. Frequency is about time cycles per second. Wavelength is about space distance per cycle.
And Zoran points out there's an inverse relationship between wavelength and frequency.
Yes. Crucially, in a given medium where the speed of sound is constant, if the frequency goes up, more waves packed into each second.
And the wavelength must go down. The waves have to be shorter to fit.
Precisely. High frequency means short wavelength.
Yeah.
The opposite is true. Low frequency means long wavelength.
He uses that serpent analogy, which is quite cool.
Yeah, the rapid tight wiggles are like short wavelength, high frequency.
While the slow, languid S-curves are like long wavelength, low frequency.
Makes it very visual. And thinking about that dragon's roar again, it's likely low-frequency components would have very long wavelengths.
And that helps it travel far.
Yes, and also helps it bend around obstacles. That's diffraction. Longer wavelengths tend to diffract more easily around things like hills or buildings.
Ah, interesting. So that low rumble can really spread out.
It can. And all these properties, speed, frequency, wavelength, are linked by a really fundamental equation.
Which is?
The speed of sound equals frequency multiplied by wavelength, V. It's core physics for waves.
Speed, frequency, x wavelength.
Right.
Got it.
And the key thing about that speed, it's not always the same.
Right. You said sound needs a medium. And the medium itself affects things.
Massively. Sound needs those interacting particles to travel. No particles, no sound wave.
So let's look at different mediums. Air, obviously, is the main one for us.
Right. And Zoran even gives us that formula for how temperature changes the speed in air. About 331 meters per second near freezing, but it gets faster as the air gets warmer.
Because the molecules are moving faster already.
Essentially, yes. They bump into each other more readily. So V equals 331.4 plus 0.6 times the Celsius temperature, roughly.
Okay. What about water?
Water's much denser than air. The molecules are packed way closer together, so the vibrations get passed along much more efficiently, much faster.
That's why whales can communicate over such huge distances underwater.
Exactly. Sound travels, Zoran says, about 4.3 times faster in water than in air. It's a big difference.
Wow. And solids, like rock or metal.
Even faster. The atoms in solids are locked really tightly together, so vibrations transmit incredibly quickly.
Like putting your ear to a railway track to hear a distant train.
Perfect example. You hear it through the metal long before you hear it through the air. Zoran mentions speeds in solids can be more than 10 times faster than in air.
Or feeling an avalanche tremor through the rock.
Before the sound arrives through the air, yeah. It shows how effectively solids transmit that vibrational energy.
Okay, air, water, solids. But what about space? the vacuum of space.
Well, that's the ultimate test of the medium requirement, isn't it? Space is, for our practical purposes, empty. Almost no particles.
No medium.
No medium, and therefore no sound transmission. The famous line, "In space, no one can hear you scream," is literally true. Profound silence, even if a star explodes right next to you.
But wait, we see stars exploding. We get light from them.
But remember, light is different. It's electromagnetic radiation.
It doesn't need a medium.
Correct. Light, radio waves, X-rays, they're disturbances in electromagnetic field, not mechanical vibrations of particles. They are transverse waves, too, oscillating perpendicular to their direction of travel. Sound is longitudinal. Big difference.
So light zips through the vacuum just fine, but sound just stops.
It can't even start, really. Without particles to push against each other, the vibration can't propagate.
So the medium isn't just incidental. It fundamentally defines the sound's behavior, its speed, how far it goes, how clear it is.
Absolutely. It shapes the entire experience of sound.
Okay, so wrapping this deep dive up, drawing on Zoran's perspective, here's something to think about. How would our whole concept, our experience of sound and communication change if we were in radically different environments? Imagine trying to communicate in, say, a thick liquid methane ocean on Titan, or the super thin atmosphere of Mars, or even within the dense plasma of a star if you could somehow survive there. How different would sound be?
That's a great question. It forces you to realize how much our reality is shaped by Earth's specific conditions, by our air. Sound isn't just hearing, is it? It's this fundamental vibration, this energy transfer moving through matter.
Exactly. It's much more than just what enters our ears. It's woven into the fabric of the cosmos, taking its character from whatever medium it happens to be traveling through.
Which brings us back to Zoran's evocative closing thought.
The universe sings its song. Learn to hear it in all its forms. Maybe we should all try to listen a bit harder, you know? Ponder those hidden harmonies, the vibrations that make up everything.
Food for thought. Until next time.
Indeed. Until our next deep dive, keep listening.